Hello everybody, this is the video for chapter 14. It's going to be a continuation of the chapter 13 video, so definitely watch that one first. So we're going to be reviewing a little bit about chapter 13 first. In the last video I talked about how an increasing glucose in the blood will cause the GLUT2 transporter to move glucose into the beta islet cells. GLUT2 is a low affinity transporter, and so the glucose has to be pretty high for this to happen, and so this makes it a good monitor of high glucose. Once that glucose comes in, of course, it's going to go through the glycolysis that we talked about in the last video. That's going to increase the ATP. The ATP is going to gate closed a potassium channel. If you don't remember that, review that from chapters 11 and 12. But closing a potassium channel is going to cause a cellular depolarization. That change in membrane potential is going to gate open calcium channels. That calcium is going to act as a signal, bind to the synaptotagmin, cause the V snares, T snares, and SNAP25 to coil up like corkscrews, and the vesicle will fuse with the cell membrane. These vesicles have been loaded up with insulin, and so then that insulin will be released from the beta islet cells in response to the high glucose. This happens in the pancreas, but the insulin gets released into the bloodstream and travels via the bloodstream to all cells that have insulin receptors. So this is an endocrine response. Endocrine being travels through the bloodstream to faraway targets. So be sure to understand the steps for how the type 2 glucose transporter, GLUT2, and its movement of glucose across the membrane in the beta islet cells of the pancreas results in the release of insulin and the systemic effect of that release of insulin. So whenever insulin is high in the blood, whenever glucose is high in the blood, insulin is released. And so now that this insulin can travel to the muscles or the liver or wherever we see insulin receptors, the insulin pathway is going to result in a lot of things like cell division, growth, changes in lipid metabolism. There's all kinds of downstream effects of insulin. One of those is the GLUT4 transporter. So GLUT4 transporter is not normally in the cell membrane. It's usually sequestered away in vesicles in the cytosol. But in response to insulin, at the insulin receptor, these muscle cells will have their GLUT4 containing vesicles fuse with the cell membrane, and so now we've increased the ability of muscle cells to uptake glucose, and that uptake of glucose allows us to clear the glucose from the bloodstream, bringing the bloodstream glucose level back down to the set point of 70 to 110 milligrams per deciliter. But once that glucose is inside of the muscle cell, then also downstream of the insulin pathway is the increase of the enzymes that are going to turn glucose into glycogen. And glycogen is the way that muscle cells and liver cells are storing the glucose. So we're taking it out of the bloodstream and putting it into glycogen storage. If the blood glucose level ever gets low, then different cells in the pancreas, the alpha cells, will secrete glucagon, and in response to glucagon signaling, the glycogen will be broken down into glucose in the liver and skeletal muscle. So, so in chapter 13, we definitely talked about the glycolysis pathway. We're just taking a 6-carbon chain and cutting it into 2 3-carbon chains. We're getting a little bit of ATP out of that and a couple of NADHs, but really the bulk of the energy is still in those pyruvate molecules. The 2 molecules of pyruvate are containing quite a bit of energy. The 2 3-carbon chains are represent the bulk of the energy still contained in the glucose molecule. So the ATP that is generated is going to be through substrate level phosphorylation. The glycolysis is a regulated pathway. We are able to turn it on and off in response to the cell's current energy state. The third step of glycolysis pathway is where we regulate it, and the molecule that we're using to regulate it is ATP. So glycolysis is going to go faster. That enzyme at step 3 is going to work faster in low ATP conditions. But ATP is a competitive inhibitor of phosphofructose kinase, the enzyme at step 3, and so in high ATP conditions, we will downregulate glycolysis. So most of the energy that you're using when you have bursts of energy is going to be using creatine phosphate. So one of the ways to store ATP for future use is through creatine molecules, and you'll have the ability to have a quick ATP response to energy use. And then when you run out of phosphocreatine, then you're in an oxygen debt. You'll need to replace that energy at a time when you're not using energy a lot. When you have extra energy, you'll replace those phosphocreatines. Just to remind you, from all the way back in chapter 3, ATP has quite a bit of energy stored in that bond between the second and third phosphate. Formally, I want you to recognize that it is not the breaking of the bond. It's not the energy stored in the bond that accounts for that 7.3 kilocalories per mole. It's actually the increase of entropy. Think back to the delta G equals delta H minus T delta S. So an increase of entropy going from one ATP molecule to one ADP molecule and one inorganic phosphate, going from one thing to 2 things, represents an increase of entropy. And so that's where we get that energy from burning ATP. And the ATP that is generated both in glycolysis as well as the citric acid cycle, or the TCA, or the Krebs cycle, or whatever you're calling it, is substrate level phosphorylation. So all that stuff that we talked about enzymes earlier back in chapter 4 and then through chapters 8 and 9. All of that stuff that we talked about how enzymes work and the bioenergetics applies to how we make ATP during glycolysis and the citric acid cycle. It's holding two things close to each other, induced fit and conformational changes, coordinating amino acids and their side chains, creating temporary covalent bonds, microchemical environment. All of that stuff is how we are producing ATP by substrate level phosphorylation in glycolysis as well as the citric acid cycle. So glycolysis happened in the cytosol, and then remember that as the pyruvate moves into the mitochondria, we talked about this in chapter 13, there's an oxidation of pyruvate to acetyl-CoA, and then that acetyl-CoA is what's going to enter into the citric acid cycle. In addition to the ATPs, we are also producing NADHs, both in glycolysis and the citric acid cycle. Those are high energy electron carriers that are going to enter into oxidative phosphorylation. So just to remind you, pyruvate, as it enters into the mitochondria, that's when we have that first CO2 generated. So we're going to take this 3-carbon chain and turn it into a 2-carbon chain, take pyruvate and turn it into acetyl-CoA through a 3-step process that generates one of the CO2s and another NADH. Now that NADH is not really going to be as useful to us in our bookkeeping, because the movement of pyruvate into the mitochondria is an active transport process. And so the NADH that we're generating here is going to get almost completely used up by the movement of pyruvate into the mitochondria. So that's the first carbon that comes off of the pyruvate molecule during pyruvate oxidation. So and of course there's 2 pyruvates, so this is going to happen twice. So 2 of the original 6 carbons of the glucose molecule have now been burned off through oxidative processes. So now we have acetyl-CoA, and acetyl-CoA is going to enter into the citric acid cycle. Now, in the absence of oxygen, we did talk about this at the end of chapter 13. In the absence of oxygen, we have to regenerate the NADs so that we can continue doing glycolysis and getting a little bit of ATP. And so, regenerating those NADs, we're going to need another oxidation reduction reaction. So NADH is going to act as a reducing agent to reduce pyruvate to lactate in us, or to reduce acetaldehyde to ethanol in yeast. But in both cases, the whole point here is to regenerate the NADs so that we can continue another round of glycolysis. So whether it is lactate fermentation in us and some bacteria, or whether it is alcohol fermentation like in yeast, in the absence of oxygen, we're going to have some way of regenerating those NADs. And so the byproducts of that are either going to be lactate, causing muscle soreness, or alcohol, which is popular with kids these days. So move on to the second video lecture for chapter 14.